What made you choose the career path you have chosen? Was it because someone strongly encouraged you to? Or was it because you had a moment in your life that made you realize there is nothing else you would rather be doing? One of the goals of our sponsor, Quanser, is to create this spark of curiosity within the general public. It is to get people to question why and how things work, and to give them an initiative to try it out themselves. So without further ado, I present to you our dancing robots.
I'm Stephen Cutler, the project manager. So this is what you got yourself into. So our project, given us by Quanser Canadian company, was to come up with a cool demo for use at different conferences. And the idea is it'd be a cool thing to connect people from different backgrounds. So it would not only attract people who are technically inclined, but it would also attract people who are artistically inclined. Next slide. So here's our team. Next slide. For our project support, we interfaced with Peter Martin on every 2 weeks or so, and he was very helpful in guiding our project. Dan Nelson was very helpful early on. We encountered a technical issue that was holding us up for a while, and he was a really good contact. Tom Lee, he came up with the idea for this project, and we really appreciate him giving us this opportunity. So these are our project requirements that we met during this project. The main takeaway from the slide, I'm not going to read them all out to you, but the main takeaway is that we met all of our minimum requirements, and we even got some extra things as well.
I'm Tyler Jordan. I worked on the beat detection part of the program. And here's the structure of the program. We have two pieces here. We have the VI that does the BPM calculation, and it sends its information to the VI that does the phase adjustment and control for the mechatronics. And so what's nice about this is it's modular, and so if we need to use a different controller, if we need to use different mechatronics, we can just swap that piece out. Likewise, if we need to use a different BPM calculator, we can do that as well. So the audio comes into the sound card, does the onset and BPM detection and the choreography generation. That's sent to the communication block, which sends it to the other VI, which is running at the same time, into the communication block, and it does the onset and phase correction there, sends it to the controller, and then that interfaces with the hardware. So we get audio in and hardware dancing out. The BPM algorithms we used we had two of them. The first one is the beat spectrum algorithm. This is by Jonathan Foote. He wrote a paper on this, and that's cited in this show, and additionally on our technical papers. And so what happens is we come in with the audio signal, which is on the top left portion of the screen, and we do a Fourier transform on intervals of it to get us the spectrogram, and so we can actually see where frequency is on the y-axis, time is on the x-axis, and the intensity is in the color. What we do is we take each new interval and compare it to all the other intervals in the current spectrogram window. This shows us the periodicity of spectral similarity, which shows how often beats will occur. Each of those comparisons is put into the similarity matrix, which is what you see on the bottom right corner of the screen. And that is calculated by taking the normalized dot product between each of the spectrogram vectors. The diagonal you see is very high return because each one, if you compare the interval 1 to interval 1, it is identically similar, and that happens along all the diagonals. But you'll also see off diagonals in the checkerboard pattern that comes with repeated beats, and those will show up as the checkerboard and the diagonals. So what we do is we actually average the diagonals of that matrix, and we get the beat spectrum, which is on the lower left portion of the screen. And you'll see those periodic beats there, and what we do is we analyze that to give us the beat. The second algorithm is the BPM spectral flux algorithm. And so we do the same thing, is that we take get the spectrogram, but then what we do is we take the derivative of that spectrogram in terms of time. We take the absolute value of that and sum them all through frequencies, sum all the frequencies of that. And that actually shows us when we have an onset of a beat, when a sharp change in a note occurs. And when we sum all those, we get the spectral flux. And both of these, you'll see, give us the same beat. And but they are good for different types of music. The beat spectrum is very good for tonal changes, where the spectral flux is very good for hard changes such as drum beats. We also see the spectral flux actually gives us the onset of beats, and we can use this in onset detection later. So we take the Fourier transform of both of those and we can get the BPM, and when those BPMs agree, we lock onto that BPM. If they do not agree, we follow either the spectral flux or the beat spectrum algorithms.
So on the phase correction portion, there are two major problems. The first one was to compensate for the lag of the system, and the second problem was to make sure that we're hitting the beats on time. So the beat and the bobbing motion occur at the same time. So the first method we used was time adjust, and the idea here was at a different point in time we would perform an adjustment for the phase lag and we'd perform an adjustment for the phase onset. The problem with this is it caused a jittery response to the dance moves, and we abandoned this way of doing it because it was aesthetically unpleasing. The second method, we used a lookup table, and we discovered that the phase lag was the same for a given BPM we were trying to follow. So if you build a lookup table, you can just adjust it as the BPM changes. The third method was to autonomously generate this lookup table to remove the manual aspect of it, and we successfully created a system that will generate a lookup table, but the problem was that the time adjustment method of calculating what the phase is was too erratic to make a table consistent enough for repeated use. The onset phase correction was done by getting a timestamp from the next expected beat and a timestamp when the VI was started. You can calculate the number of periods between those two timestamps, calculate the remainder, and use that to figure out what the phase correction should be.
Kuskov and I, Jasmine Pedroza, were in charge of making things a bit more interesting by incorporating different dance moves. The three dance moves we came up with were the bob, sidestep, and spin. These three moves could be monitored by the user, which you can see by the use of the switches. We have 3 switches. The amplitude switch is in charge of taking care of the bob. The spin and the sidestep are obviously taking care of the spin and the sidestep. So the first switch we have is amplitude. The amplitude is energy dependent, and what it does is it takes the energy sum of the song and then it will group it up into different sections. Depending on the amount of energy that is showing, it will adjust the amplitude of the bob. So if you're playing a calm song like Jack Johnson, it'll have a small bob, whereas if you're playing a heavy metal song, the amplitude will increase and imitate a jumping motion. The next switch we have is the spin. The spin is BPM dependent, and what it does is it will keep track of the BPM. When there is a drastic change, the helicopter will stabilize itself, stay horizontal, and do a 360-degree spin. If the BPM is within range of about 8, then it will not spin, but if it's greater than that, then it will. The last switch we have is the sidestep. The sidestep is also BPM dependent. What it does is it will store BPM values for a number of seconds. If the values are within range of each other, then it'll do a sidestep. And what that is it'll bob a couple of times, step to the side, and then continue to bob. For the inverted pendulum, the only 2 moves that we had time to implement were the dance amplitude correlation and the sidestep. Unfortunately, we couldn't implement the spin in time, with the time that we had.
My name is Artem Kuskov, and as Jasmine just pointed out, we were working on the dance moves for the helicopter and the inverted pendulum. We ran into some challenges whenever we were trying to implement that. First, challenge was the hardware boundaries and degrees of freedom. We weren't able to make the robots do whatever we wanted to because of the hardware limitations, and that was the biggest challenge. The second challenge that we had is combining the dance moves. Once we created the dance moves and separately they were working great. However, when we tried to combine them, it was very hard to decide which dance moves happens first, which one happens last, and also we had to put the boundaries. When one dance move is getting executed, the other one couldn't even start. Once we were done with detecting the beat, correcting the phase, and detecting the dance move, we had to communicate to the controller program. Quanser provided us with a nice communication block that we were able to use to transmit data from the BPM detection algorithm to the controller side. After detecting the BPM and selecting the dance move and having everything controlled, we had to test the system. First test that Quanser required us with was the 30 seconds of music following. We passed it with no problems. The second challenge was to test 3 different songs with 3 different BPMs and rhythms, and that test passed as well because we actually have 2 algorithms that are developed to detect different beats. Our code evaluation was done by Peyton Martin, and he was pleased with that. For aesthetic evaluation, we put the video of the inverted pendulum on YouTube and read the comments about how we had it perform. The performance criteria was done by our sponsor, Dr. Lee, and he was thrilled about our results. We completed all the deliverables that we had for class and for our sponsors,